Okay, so ready for a deep dive into something pretty fundamental.
Always up for a challenge.
Hmm.
Where are we headed today?
Well, we're going to be looking at organic chemistry.
Organic chemistry.
Mm.
The land of carbon, right?
Yeah, exactly. And specifically, these incredible carbon compounds that we get from crude oil.
Ah, this stuff that basically powers and builds our modern world.
You got it. And what's really fascinating is how we can take this kind of raw, unprocessed material and turn it into so many of the things we use every single day.
Yeah, it's quite a transformation from that thick, black, gooey stuff to the fuel in our cars to the plastic in our phones.
Absolutely. So maybe we should start with the basics. What exactly is crude oil?
Well, I think a lot of people would be surprised to learn that it all starts with these tiny little sea creatures called plankton that lived millions of years ago.
Oh, right. Like the base of the food chain in the oceans.
Yeah, exactly. So when they died, they sank to the ocean floor
Yeah.
and got buried under layers and layers of mud and sediment
Like over millions of years, right?
over vast, vast amounts of time. And under this incredible heat and pressure, their remains were slowly transformed into this substance we call crude oil.
Which we now find trapped in rocks deep underground.
Exactly. And it's a finite resource. You know, we can't just make more of it.
Which is a pretty important point to consider.
Absolutely. And it's not just one single thing, is it? It's more like a really complex mixture. Think of it like a massive natural chemical soup.
Chemical soup.
Yeah, full of all sorts of different ingredients, all mixed together, but crucially not chemically bonded. They're just kind of jumbled up together.
Which means we can separate them out using physical methods?
Precisely.
So what are the main ingredients in this ancient plankton soup? I know you mentioned carbon.
Right. Well, the main players are these things called hydrocarbons. And the name kind of gives it away. Hydro for hydrogen and carbon for, well, carbon.
So compounds made up solely of hydrogen and carbon atoms.
Yep. And the most common type of these in crude oil are what we call alkanes. Yeah. Alkanes are saturated hydrocarbons. Think of it like they're fully satisfied because they only have single bonds between the carbon atoms.
Okay. And is there like a way to represent this, like a formula that applies to all alkanes?
Absolutely. They all follow a general formula, CnH₂n+₂.
Okay, and that little N stands for?
The number of carbon atoms in the molecule. So let's look at some examples. The simplest alkane is methane with just one carbon atom.
So N1 in that case.
Exactly. So plugging that into the formula, we get CH4, one carbon, and four hydrogens.
Okay, got it. What about ethane? Two carbons.
That's right. So N to 2, and the formula becomes C2H6.
Two carbons and six hydrogens. Okay, I think I'm getting the hang of this. What's next?
Propane. Three carbon atoms, so N to 3, which gives us C3H8.
Which rings a bell. Isn't that what they use in camping stoves?
It is, yeah.
I know.
Well, that's butane. This one has four carbon atoms, so N to 4, and we get C4H10.
Butane. That's the stuff in lighters, right?
That's the one. And here's a little trick to help you remember the first four. Monkeys, peanut butter methane, ethane, propane, butane.
Haha, love it. But we're getting a bit ahead of ourselves. We've got this crude oil, which is a mix of all sorts of different hydrocarbons all jumbled up. So how do we actually separate them out?
Well, that's where a really nifty process called fractional distillation comes in. It's one of the cornerstones of the petrochemical industry.
Okay, fractional distillation. What's the basic idea behind it?
It all boils down to the fact that these different hydrocarbons have different boiling points. The bigger the molecule, the higher the boiling point.
Right, makes sense. So how does that help us separate them?
Well, imagine we heat up this crude oil. It's all going to turn into a gas,
Yeah.
vaporize.
Okay, got it.
Now, this hot vaporized oil rises up a tall tube that we call a fractionating column. It's really hot at the bottom and gradually gets cooler as you go higher.
So it's like a temperature gradient?
Exactly. As this vapor travels up the column, the temperature starts to drop, and different hydrocarbons will start to condense back into liquids at different heights, depending on when they reach their boiling point.
So the ones with higher boiling points will condense lower down in the column.
That's right. It's because they don't need to cool down as much to turn back into a liquid. It's all about intermolecular forces, the forces of attraction between the molecules.
The stickiness between them, right?
Yeah, you could say that. The bigger molecules have stronger intermolecular forces, so they stick together more readily, and they don't need to rise as far up the column to cool down enough to condense.
Okay. And the smaller molecules?
Well, they have weaker intermolecular forces, so they need to travel further up the column where it's cooler before they condense.
So at different levels along this column, we can collect these different fractions, right?
Exactly. And each fraction contains hydrocarbons that have a similar number of carbon atoms and therefore similar boiling points.
So this whole thing runs continuously with more heated crude oil constantly being piped in at the bottom.
That's right. It's a really elegant and efficient way to separate this complex mixture.
And what do we actually do with these fractions once we've got them?
Well, some of these fractions are used directly as fuels. The fuels that power pretty much everything. Petrol for cars, diesel for lorries and trains, kerosene for airplanes, even the thick, heavy fuel oil used in big ships. And don't forget those liquefied petroleum gases, things like propane and butane.
Right, like what we were talking about earlier for camping stoves.
Exactly. But it's not just about fuels, is it? These fractions also serve as the starting material, the feedstock, for the petrochemical industry.
Right, so they're the raw ingredients that are chemically transformed into all sorts of other useful stuff.
Exactly. Think solvents, which are used in paints and cleaning products, lubricants, which help reduce friction between moving parts in all sorts of machines, and then polymers.
Polymer.
Yeah, these are massive molecules, long chains of repeating units that make up all kinds of plastics and synthetic fibers, like nylon. Even things like detergents, which help us clean our clothes, are made from petrochemicals.
It's quite amazing how many different things come from this one initial resource. And it really shows how versatile carbon is. It can form these whole families of similar compounds, right? We call those homologous series, don't we?
We do, and that's what allows for such a massive diversity of both natural and man-made carbon-based molecules.
So what determines which hydrocarbon fraction is good for, say, fuel and which is better for making plastics? Is it just down to those different boiling points that we talked about earlier?
Well, as we touched on with fractional distillation, there are several key properties that depend on the size of their molecules. And these properties are really important, especially when we think about using them as fuels.
Okay, let's talk about these properties. What are some of the main ones?
Well, one is viscosity. Think about how runny a liquid is.
Okay, like water is very runny, honey is less runny, that kind of thing.
Yeah, exactly. So shorter hydrocarbon molecules tend to be less viscous. They flow really easily, like petrol.
Okay.
But longer molecules are much more viscous, thicker, and stickier.
Like the heavy fuel oil used in ships that you mentioned.
Precisely. And then you've got boiling point and the temperature at which they condense back into a liquid.
And as we said, the bigger the molecule, the higher the boiling point.
Exactly. And that's all related to those intermolecular forces, that stickiness between the molecules. Shorter molecules have weaker forces, so they need less energy to break free and become a gas.
So they have lower boiling points.
Exactly.
And the longer molecules with stronger forces, they have higher boiling points.
That's right. And then there's flammability, how easily they catch fire, which is pretty important when it comes to fuels, right?
Yeah, absolutely. And I guess this also relates to molecule size.
It does. Shorter hydrocarbon molecules are generally much more flammable.
They ignite more easily.
Yeah, much more easily. Think about trying to light a thick oil compared to something like methane or butane, which we said was in lighters.
Right, huge difference.
Absolutely. And the reason we burn hydrocarbons as fuels in the first place is because that reaction, combustion, releases a significant amount of energy. That's the heat that powers our engines and generates electricity.
Right, and we know that to burn something, you need oxygen, so what's actually happening in this combustion reaction?
Well, the general equation is this. A hydrocarbon reacts with oxygen in the air, and that produces carbon dioxide and water.
So the hydrogen and carbon atoms in the hydrocarbon are both reacting with the oxygen, right? They're being oxidized.
That's right. And if we have plenty of oxygen, that's what we call complete combustion.
So in complete combustion, the only products are carbon dioxide and water.
Precisely. Now, we've talked about how fractional distillation is great for separating crude oil into these different fractions based on their boiling points. But sometimes the amounts of each fraction we get from crude oil don't really match up with what we need.
Right, so we might end up with a lot of one fraction, but not enough of another.
Exactly. We might have loads of those longer chain hydrocarbons, but need more of the shorter chain ones, like petrol.
To keep all those cars running.
Precisely. And that's where this really clever process called cracking comes in.
Cracking sounds a bit intense.
It's a way of deliberately breaking down those larger, less in-demand hydrocarbons into smaller, more useful ones.
Okay, so we're taking those long chains and cracking them into shorter ones.
Exactly. And this gives us more of the fuels we need, like petrol.
So how do we do this cracking? What actually happens?
Well, there are two main methods: catalytic cracking and steam cracking.
Okay, so tell me about catalytic cracking first.
In this method, we heat up the long-chain hydrocarbons, turn them into a gas, and then pass these hot vapors over a special material called a catalyst.
That catalyst. So something that speeds up the reaction.
Exactly, without being used up itself in the process. A common catalyst used in cracking is aluminum oxide. And this catalyst helps to break the bonds in those large hydrocarbon molecules.
And what about the other method you mentioned, steam cracking?
Well, in this method, we mix the vaporized long-chain hydrocarbons with steam, just water in its gaseous form.
Okay.
And then we heat this mixture to a very high temperature.
To break those bonds.
Exactly. This intense heat basically provides the energy for those molecules to shake themselves apart, a process called thermal decomposition.
Okay, I see. So regardless of the method, we end up with smaller hydrocarbon molecules.
That's right. But here's a key point. Cracking doesn't just produce alkanes, those saturated hydrocarbons we talked about earlier. It also produces another really important type of hydrocarbon called alkenes.
Alkenes.
Yeah, alkenes are unsaturated hydrocarbons, which means they contain at least one carbon-carbon double bond.
Ah, so that's the key difference, the double bond.
Exactly. And this double bond changes how alkenes behave chemically. The general formula for alkanes is CnH₂n.
Okay, so two fewer hydrogen atoms compared to alkenes.
That's right. And the simplest alkene, with 2 carbon atoms, is ethene, C2H4.
And after ethene, we have?
Propene, with 3 carbon atoms, C3H6.
So the big difference between alkanes and alkenes is that double bond.
Yep. Alkenes are saturated. They only have single carbon bonds. They're holding as many hydrogen atoms as they possibly can.
Like they're full up.
Exactly. But alkenes with that double bond are unsaturated. If that double bond was broken, they could bond with more hydrogen atoms.
Interesting. So this double bond makes them more reactive.
It does, yeah. It's where a lot of the interesting chemistry of alkenes happens. And in fact, there's a simple test we can do, something you might even do in a school lab, to tell alkenes and alkenes apart. It's called the bromine water test.
Bromine water test, what's that?
Well, bromine water is this orange-colored solution. If you bubble an alkene through it, the bromine reacts with the double bond, and the solution loses its color. It becomes colorless.
Ah, so it's a visual test.
Exactly.
Yeah.
But if you bubble an alkane through it, nothing happens. The solution stays orange because alkenes don't have that reactive double bond.
That's really neat, a really clear way to see the difference. So alkenes are not just useful as fuels themselves, they're also important starting materials for making other chemicals, right? Like those polymers you mentioned for plastics.
Absolutely. And going back to fuels for a moment, some of those smaller alkanes and alkenes we get from cracking are actually really good fuels because their shorter chains make them more flammable. They burn more easily.
Okay, makes sense. Now, when we talk about cracking, we often see chemical equations to show what's going on, how the molecules break down. How do we know if those equations are balanced, if they're showing what's really happening?
Well, it's the same fundamental principle for any chemical reaction. The total number of atoms of each type of element must be the same on both sides of the equation.
Okay, so it's like a before and after picture, and nothing's gone missing.
Precisely. If you start with, say, a hydrocarbon that has 6 carbon atoms and 14 hydrogen atoms, the products of the cracking reaction must also add up to a total of 6 carbons and 14 hydrogens. Nothing can just disappear.
Right, so it's all about balancing the equation. Can you give me an example of that?
Sure. Let's say we crack hexane, which has the formula C6H14, and one of the products is ethene, C2H4. What would the other product be?
Okay, so we started with 6 carbons, and ethene has 2, so there must be 4 carbons left. And we started with 14 hydrogens, ethene has 4, so there are 10 left over. So the other product must be C4H10.
That's right.
Which is butane. So cracking hexene can give us ethene and butane.
Okay, I get it. Now, we've talked a lot about alkenes and how that double bond makes them so reactive. What kind of reactions can they undergo?
Well, there are quite a few, but one of the most characteristic is addition reactions.
Addition. So we're adding something to the molecule.
Exactly. Think about that double bond. We can break one of the bonds, and that creates 2 available bonding sites, one on each carbon atom. Okay, so it's like opening up the molecule.
Yeah, you can think of it that way. Then we can add new atoms or groups of atoms to each of those carbon atoms. So the double bond becomes a single bond, and we've added something new.
Can you give me an example of an addition reaction with an alkene?
Sure. Let's take ethene C2H4 and react it with bromine, Br2.
Bromine. That's the stuff that's a liquid at room temperature, right?
Yeah, it's a reddish-brown liquid. So in this addition reaction, the bromine molecule splits, and each bromine atom attaches to one of the carbons in the ethene, forming dibromoethane.
Okay, so we've added 2 bromine atoms across that double bond.
That's right. And we could do similar things with other molecules like hydrogen. That's called hydrogenation.
So if we reacted ethene with hydrogen, we get ethane.
You got it. The double bond becomes a single bond, and we add those two hydrogen atoms. It's a way of converting an alkene back into an alkene.
Like we're saturating it again.
Exactly.
Can we add other things, like water?
We can. That reaction is called hydration, and it usually needs a catalyst, something to speed up the reaction, like an acid.
Yeah.
The water molecule adds across the double bond, so you end up with an HOH group attached to one of the carbons, which means you've made an alcohol.
So if we added water to propene, we'd get propanol.
That's right, and we can do addition reactions with other halogens too, like chlorine or iodine.
So basically, we can add all sorts of things across that double bond in an alkene.
Yeah, that's the key.
So we've seen how we can get alkenes from cracking crude oil. And we know that by adding water to an alkene, we can make an alcohol. So let's talk about alcohols specifically. What makes an alcohol an alcohol?
The key feature of an alcohol is the hydroxyl group, which is written as HOH. It's an oxygen atom bonded to a hydrogen atom.
Okay. And that little AQH group, that's what gives alcohols their specific properties.
Exactly.
We've learned about the first four alkanes, and the first four alkanes, what about the first four alcohols?
Well, you already mentioned one, propanol. The first four are methanol, CH3OH, ethanol, C2H5OH, propanol, C3H7OH, and butanol, C4H9OH.
Ah, I see they all have that OH group attached to the carbon chain.
That's it. And notice how their names all end in ol. That's how we identify alcohols.
Handy tip. So what kind of things can alcohols do? How do they react?
Well, like most organic compounds, they can burn in air, reacting with oxygen to produce carbon dioxide and water, releasing energy.
Okay, that's combustion.
Right. They can also dissolve in water, which is a bit different from some other compounds that contain the OH group.
Oh, really? Why is that? I thought the OH usually makes things alkaline.
It does in things like metal hydroxides, but in alcohols, that OPOH group is covalently bonded to the carbon chain.
Okay, so the oxygen and hydrogen atoms are sharing electrons. It's not an ionic bond like in the hydroxide ion.
Precisely.
So alcohols dissolve in water to form neutral solutions. What else can they do?
Well, they can also react with some reactive metals, like sodium, and when they do, they release hydrogen gas.
Ah, a bit like how acids react with metals.
Kind of. And you'll also get a salt formed, called an alkoxide.
An alkoxide.
Yeah, so if you reacted ethanol with sodium, you'd get sodium ethoxide and hydrogen gas.
Interesting. I think you also mentioned earlier that alcohols can be oxidized.
Right. When we oxidize an alcohol, it reacts with an oxidizing agent.
Which is something that can add oxygen or remove hydrogen, right?
Yeah. And when an alcohol is oxidized, it gets converted into a carboxylic acid.
Another family of organic compounds to add to the list.
Exactly. And the specific carboxylic acid you get depends on what alcohol you started with.
So lots of different possibilities.
Definitely. So we've got these first four alcohols. What are some of their uses?
I know ethanol is in drinks, but what about the others?
Well, methanol is used as a starting material to make other chemicals. It's a feedstock, like we were saying earlier about the fractions from crude oil.
Mm.
And it's also used in antifreeze to lower the freezing point of water in car radiators.
Keeps those engines from freezing up in winter. And you can also use it to make biodiesel.
That's right. Biodiesel is a type of renewable fuel, an alternative to diesel made from crude oil.
Cool. And ethanol, besides being the alcohol in alcoholic drinks, it's also a good solvent and can be used as a fuel itself.
It can. And interestingly, all four of these alcohols we've mentioned, they can all be used as fuels in various applications.
And we can even make ethanol without using crude oil, can't we? It's made in that process called fermentation.
Right. Fermentation is a biological process that uses yeast to convert sugars into ethanol and carbon dioxide.
The yeast is like eating the sugar.
In a way, yeah. Needs certain conditions to work properly, though. It needs to be warm, around 35 degrees Celsius, and it needs to be anaerobic.
Anaerobic, meaning no oxygen.
Exactly. And we use enzymes in the yeast as catalysts to speed up the reaction.
Okay, so fermentation is a pretty neat way to produce ethanol using renewable resources. Now, we've mentioned carboxylic acids a few times. Let's unpack these.
Okay, so carboxylic acids are another important group of organic compounds. They all have this functional group, which we write as COOH.
The carboxyl group. And that's what gives them their characteristic acidic properties.
Right.
What about some examples?
Well, the most familiar one is probably ethanoic acid.
Ethanoic acid, that's what gives vinegar its sour taste, isn't it?
That's the one. The first four carboxylic acids are methanoic acid, ethanoic acid, propanoic acid, and butanoic acid.
And they all have that NES-COH group in their structures.
They do.
So what are carboxylic acids like? How do they behave?
Well, the most obvious property is that they're acidic, When you dissolve them in water, they release hydrogen ions, which makes the solution acidic.
Okay, so the pH of the solution is less than 7.
Exactly. They also react with carbonates, like metal carbonates, releasing carbon dioxide.
Which is that classic test we do in the lab, turning lime water cloudy.
That's right. And carboxylic acids can also react with alcohols to form esters.
Esters, what are those?
Esters are a family of organic compounds that often have pleasant, fruity smells. And to make an ester, you need to react a carboxylic acid with an alcohol. It's a condensation reaction.
Right, condensation, like water being squeezed out.
Exactly. Now, it's really important to remember that carboxylic acids are weak acids. They don't fully ionize when you dissolve them in water.
Right, so they only release some of their hydrogen ions.
That's it. Which means the concentration of hydrogen ions in the solution is lower compared to a strong acid of the same concentration. So their pH is higher, meaning they're less acidic.
Okay. We've covered so much, from crude oil to cracking to all these different families of organic compounds. But there's one big topic we haven't touched on yet, and that's polymers.
Ah, the giants of the molecular world.
Exactly. Polymers are so important, so prevalent in our everyday lives. Plastics, fabrics, they're everywhere. So what are they? What makes a polymer a polymer?
The key thing about polymers is that they're really big molecules, really long chains made up of lots of smaller repeating units called monomers.
So monomers are like the building blocks.
Exactly.
And how do these monomers actually join together to make these giant molecules?
Well, there are two main types of polymerization reactions: addition and condensation.
Okay, let's start with addition polymerization.
All right, addition polymerization usually involves alkanes, those molecules with the carbon double bond. And in this reaction, the monomers join together without losing any atoms.
So nothing is given off as a byproduct?
No. The double bond in each monomer opens up, and those electrons are used to form new single bonds, linking all the monomers together in this long chain.
Can you give an example?
Sure. The classic example is polyethylene.
The stuff plastic bags are made of.
That's it. Polyethylene is made by joining together loads of ethene molecules.
So lots of small ethene molecules all linked up to form one massive molecule.
Exactly. The double bond breaks, and the carbons form single bonds with their neighbors. And the repeating unit has the same atoms as the ethene monomer. We usually draw polymers with the repeating unit in brackets, with bonds extending out, and then an N outside the brackets to show that it repeats many times.
Right, that N is like saying, and so on and so forth.
Exactly. Now, condensation polymerization is a bit different.
How so?
In this type of polymerization, the monomers also have two functional groups, but when they join up, they lose a small molecule, usually water.
Okay, so there's a byproduct this time.
Right. And often condensation polymers are formed from two different monomers, each with two of the same functional group.
Let's see.
A good example is polyesters.
Polyesters. That's in lots of clothing, isn't it?
It is. And polyesters are made from monomers with two carboxylic acid groups and monomers with two alcohol groups.
And when they react, they lose water, right?
Right. A water molecule is formed for every new bond formed in the polymer chain. And the link between the monomers is called an ester linkage.
Ah, so that's where the name polyester comes from.
Exactly. And this idea of condensation polymerization, it's not just for making things like polyesters. It's also how some really important biological molecules are made.
Like what?
Well, polypeptides, for example.
Polypeptides, that rings a bell from biology.
They're the building blocks of proteins. And to make a polypeptide, you join amino acids together.
Amino acids are the monomers.
Exactly. And amino acids have two different functional groups, an amine group and a carboxylic acid group. When they join together, they lose a water molecule and form what we call a peptide bond.
Just like in the formation of a polyester?
Yeah, very similar idea, just different functional groups involved.
Amazing. And what about DNA? You mentioned that earlier. Is that a polymer too?
DNA, or deoxyribonucleic acid,
Yeah.
is absolutely a polymer. It's a huge molecule, two strands twisted around each other in a double helix, and it carries our genetic code.
Our genetic blueprint.
Exactly. And each strand is made of monomers called nucleotides. There are 4 different types of nucleotides, and the order they're arranged in is what encodes all the genetic information.
Incredible. So from plastic bags to the molecules of life, it's all about polymerization.
It is. And there's some other really important natural polymers like starch and cellulose. You've probably heard of those.
Yeah, definitely. Aren't they both made of glucose?
That's right. They're both plant-based polymers. Starch is how plants store energy, and cellulose is what gives them their structural strength. It's the main component of plant cell walls.
Right. So whether we're talking about synthetic materials or the molecules essential for life, it all comes back to this idea of monomers joining together to form these long chains. It's really quite
It
mind-blowing.
is, and it all comes back to carbon.
Carbon, the element of a million possibilities.
Exactly.
Well, this has been a fantastic deep dive into organic chemistry. We've gone from the origins of crude oil as the remains of ancient plankton, to how we separate it using fractional distillation, to how we crack those hydrocarbons into smaller molecules, and then to the reactions of alkenes, alcohols, and carboxylic acids. And we've seen how all of this leads us to the world of polymers, both those we make and those that are the basis of life itself.
It really is a remarkable journey from those simple hydrocarbons to such an array of materials.
And it makes you appreciate where everything comes from. So as we wrap up, here's something to ponder. We've learned that crude oil is a finite resource, and we've seen how important the materials we get from it are. So what happens when it runs out?
That's the big question, isn't it?
It is. So what about sustainable alternative? Can we find new ways to make these essential compounds without relying on crude oil? What innovations are on the horizon? It's something to think about. And next time you're using a plastic bottle or filling your car with petrol, think about where those materials came from and what the future holds. Thanks for joining us.
Great deep dive.